Hello and welcome to the User-Defined Functions training course, proudly provided by Mr. CFD Company. Our comprehensive curriculum covers all aspects of academic and industrial simulations, ensuring you will leave with the knowledge and skills needed to excel in this field. This course is divided into two essential chapters. The first chapter will cover the fundamental basics of user-defined functions and their importation into ANSYS Fluent software. The second chapter will focus on performing important tutorials that demonstrate the various applications of UDF in ANSYS Fluent. It's imperative that you stay with us to fully grasp the concepts presented in this course. Today, researchers use the ANSYS Fluent software in the field of computational fluid dynamics simulation. Fluent is used for fluid and thermal modeling in various engineering fields such as mechanical, aerospace, medical, HVAC, rotating objects, and more. This software is comprehensively designed and can address most of the needs of engineers and researchers. However, sometimes we encounter problems that are examined in very specific engineering applications. To simulate such issues, we cannot directly use Fluent software. However, one of the special features of Fluent is that it allows for user software programming to meet any need. In other words, the user is allowed to write macros and programs and link them to the software, expressing their request in the form of commands to the software. In Fluent software, this capability is accomplished using a UDF or user-defined function. UDFs are functions written in the form of a text program to enhance the usual capabilities of Fluent and are applied to the software. The text commands of the UDF file are written in the C or C++ programming language. UDFs are used in many applications in the numerical solutions of Fluent software. Here, we mention a few common and important uses of UDFs. Using UDFs for specific boundary conditions in the problem such as velocity and temperature profiles etc. based on location or time. Using UDFs to define the thermophysical properties of the fluid such as viscosity and density based on a specific relationship. Using UDFs to create source terms in governing equations like a source term in momentum equations or energy equation. Using UDFs to define the motion of rigid bodies in dynamic mesh models. Using UDFs to define the surface rate and volumetric rate of chemical reactions in the equations of chemical processes. Using UDFs to create source terms in user-defined scalar transport equations, and many other cases. In general, Fluent software allows the users to use UDFs in many cases during the numerical solution process by the software. This image illustrates the process of solving a numerical simulation by Fluent. This image shows in what situation the user can influence the numerical solution of the software by creating a UDF. There are two methods to execute a UDF program in Fluent software. The first one is interpret method. UDF files are loaded directly and in a single step process at runtime. The second one is compile method. This method involves a two-step process where a shared library file is first created and then loaded into the ANSYS Fluent software. When we compile a UDF file, the written code is converted into a series of library files with .dll extension to be executable on Fluent software. In fact, these created library files are a translation of the C or C++ program to be understandable by Fluent. To generate these library files, we need to click on the build option. Then these library files are connected to Fluent software, and after loading these files into the software environment, all commands related to the written code are transferred to the case file of the model in question. To load these files, we need to click on the load option. However, when we interpretively call a UDF file, we directly use the original language program in C or C++ and functions and macros understandable by Fluent software. In fact, at the time of calling UDF in Fluent, the original language code is converted into a code understandable in Fluent and then executed in Fluent. To call these files, we need to click on the Interpret option. We can summarize the important points in writing UDF programs for execution in Fluent as follows. UDF containing programs must be written in the C or C++ programming language. UDF programs must be defined using the define macros provided by Fluent software. In other words, the user is only allowed to use the macros defined by Fluent. In the first line of the program, the phrase hash include UDF.h must be written. This command links and establishes a connection between the UDF program and Fluent software so that the program can be defined in Fluent. These UDF programs are executed in Fluent by two methods, interpretive and compiling. UDF programs are linked to Fluent software by the graphical user interface panels available in the software environment. UDFs use data from Fluent software for their calculations. That is, UDFs receive a set of data from the Fluent software. This data or internal variables of the software are defined based on expressions from the computational mesh components. Therefore, before writing the desired UDF program, we become familiar with mesh terminology in Fluent software. In Fluent software, each computational mesh is divided into a series of control volumes. These control volumes represent cells that are enclosed by faces and nodes. Fluent software uses internal data structures to define the domains of the mesh, assign commands to cells, cell faces, and nodes within the mesh, and establish connections between adjacent cells. We aim to examine the meshing of computational region in two-dimensional and three-dimensional cases. In this image, you observe a two-dimensional mesh. This mesh is composed of several two-dimensional cells, each of which is formed by several nodes and faces and has a cell center. However, in this image you observe a three-dimensional mesh. The difference between two-dimensional and three-dimensional meshing is that the cells are volumetric and the faces are planar. Also, the mesh lines are in the form of edges. Now we want to get acquainted with the widely used concept in structured data called a thread. A thread in Fluent software is considered a data structure used to store information related to a boundary or cell region. In fact, the threads are used in the UDF program so that the UDF can access and store the information related to the mesh of the computational region of the desired model in Fluent. It can then apply and use this in the relevant UDF. In other words, access to information about surfaces or cells in the Fluent data structure is provided through the definition of a thread. Cell threads are made up a group of cells, while face threads are made up of a group of faces. This image refers to a three-dimensional mesh. Therefore, cell threads are composed of several volumetric cells that form the computational domain of the model, whereas face threads consist of several planar surfaces that include the boundaries of the model. This image refers to a two-dimensional mesh. Cell threads and face threads are defined as before. However, in a two-dimensional model, cell threads are composed of several planar surfaces that form the computational domain of the model, whereas face threads consist of several linear edges that include the boundaries of the model. To access the information of the threads, we must use pointers. Pointers to thread data structures are passed to ANSYS Fluent's internal functions and manipulated to gain access to the information related to the boundaries or cell regions provided by each thread. Note that each boundary or cell zone that we define in our modeling has an ID number in the boundary condition settings panel in the Fluent software environment. This ID represents an address for the information inside that zone. However, you will not see the term thread in the Fluent software setting panel. So, when programming a UDF, you can imagine a zone as being similar to the data structure of a thread. So, in general, computational grid data structures are used to access information from different regions, for example, input and output boundaries, walls, fluid regions, and etc. These data structures are briefly defined as follows. Node, a point or node of the grid. Node thread, a group of nodes. Edge, the edge or boundary of a surface in a 3D model. Face, the boundary of a cell, surface in a 3D model or edge in a 2D model. Face thread, a group of surfaces, same as the surface thread. Cell, a control volume into which the computational domain is divided. Cell thread, a group of cells. Cell center, the spatial position of the cell center where cell data is stored. Domain, a group of nodes, surfaces, and cells. In this image, we have briefly illustrated the introduced data structures in the computational grid model. Some of the data types that exist in C and C++ programming languages are also used to define data in UDF programming. However, in addition to these data types, there are a few other data types that are specific to Fluent software. These data types are related to the Fluent computational grid structure. Variables defined by these data types are generally provided as an argument for defined macros as well as other spatial functions that have access to ANSYS Fluent solver data. Some of the most commonly used data types in ANSYS Fluent include node. This is a type of data structure that stores information related to a node of the network. Face _t. This is a data structure in the form of an integer that defines a specific surface within a string of surfaces or cell thread. In other words, we have several surfaces in the form of a surface thread, and we want to select one surface from among these surfaces. Cell _t. This is a data structure in the form of an integer that defines a specific cell within a string of cells or cell threads. In other words, we have several cells in the form of a cell thread and we want to select one cell from among these cells. Thread. This is a type of data structure that stores information related to a group of surfaces or cells. For multi-phase flow problems, a separate thread is defined for each phase of the mixture. Domain. This is a type of data structure that encompasses information related to a set of node threads, surface threads, and cell threads in a computational grid. For single phase flows, there is only one domain, while for multi-phase flows, there can be multiple domains. Here you see a summary of how data is defined in UDF programming. Domain *D, where D represents a pointer to the domain thread. That is, it's a means of accessing the domain data structure information. Thread *T, where T represents a pointer to the thread. That is, it's a means of accessing the thread data structure information. Cell _TC, where C is equivalent to the cell index variable. That is, the information of the selected cell from the cell thread is placed in this variable. In other words, a thread is formed from several cells, and the information of each of these cells is placed in a variable named C. Face underline TF, where F is equivalent to the surface index variable. That is, the information of the selected surface from the surface thread is placed in this variable. In other words, a thread is formed from several surfaces, and the information of each of these surfaces is placed in a variable named F. Note *n, where n represents a pointer to the node. That is, it's a means of accessing the node data structure information. To define a UDF, we must use a series of defined macros. Defined macros are predefined macros prepared by ANSYS to be used for defining UDFs. In other words, ANSYS Fluent software provides a set of macros to assist its users in defining the functions they need. In fact, each defined macro is used to define a specific function for use in a specific part of the Fluent software. We intend to introduce you a list of commonly used defined macros and have a useful discussion about each one. We have also tried to provide a UDF code sample for some of the commonly used macros to familiarize you well with the use of these defined macros. We use UDF programming in many sections of the Fluent software environment, so there are a very large number of defined macros available. Therefore, we provide a general categorization of macros, which is as follows: general purpose defined macros, model specific defined macros, multi-phase defined macros, discrete phase model defined macros, dynamic mesh defined macros, and user defined scalar transport equation defined macros. Now we introduce each group of macros in turn. First, we introduce the general purpose defined macro. These macros relate to functions that are independent of the models used in ANSYS Fluent software. Here, we introduce some of the general purpose defined macros. Define adjust macro, used for manipulating, changing, and adjusting variables. Define delta t macro, used to determine the time step only in time dependent or transient solutions. Define execute at end macro, used to execute and comment at the end of the desired iteration. Define init macro, used to initialize variables. Define on demand macro, used to execute and comment at the user's demand. Define RW file macro, used to read or write variables in old case and data files. For example, the define adjust macro is a function that is called at the start of each iteration of the solution process and exactly before the transport equations are solved by ANSYS Fluent. This function is used to adjust few variables, compute integrals, and so on. This macro is represented using two arguments. The first argument indicates the name of the function, and the second argument is a pointer to the domain of the model on which the adjust function is applied. This domain pointer allows access to the information of all cells and string surfaces in the desired computational domain mesh. To activate this function and link it to the software, you need to go to this path and define the function as a UDF for the software. It should be noted that the UDF in question appears in the Fluent software with the same name that we defined in the first argument of the defined macro. To activate the UDF function, you should first call the desired UDF function in the Fluent software. Then go to the part of the software environment where the UDF function is to be applied. And finally, activate the called UDF in the appropriate place. So, first from the Define tab, go to the User Defined section and select the function option. From the appeared menu, select the compile option. With this action, the desired UDF function is called in the Fluent software. Then, in the same user-defined section, select the function hooks option. Now, in the appeared menu, go to the adjust option so that in this section you can select and activate the called UDF function. In another example, we introduce the define delta t macro, which is used to determine and control the time step in unsteady problems. This function applies the size of time step as a real number for the software. This macro is represented using two arguments. The first argument indicates the name of the function, and the second one is a pointer to the domain of the model on which the time step control function is applied. That is, the pointer to the domain allows access to the information of all cells and thread surfaces in the desired computational domain mesh. To activate this function and link it to the software, you need to go to this path and define the function as a UDF for the software. It should be noted that the UDF in question appears in the Fluent software with the same name that we defined in the first argument of the define macro. To activate the UDF function, you first need to call the desired UDF function in the Fluent software. Then go to a part of the software environment that is supposed to apply the UDF function to ultimately activate the called UDF in the appropriate place. So first, go to the define header, go to user defined and select the function option. From the appearing menu, choose compile. This will call the desired UDF function in the Fluent software. Then in the run calculation section, go to the type section to specify how to define the time step. So choose the user defined function option. So in the menu of the user defined time step size section, the called UDF function is activated. In another example, we examine the define execute at end macro. This macro is executed at the end of each iteration of a steady state solution or at the end of each time step of a transient solution. In fact, this function is used when the user intends to perform calculations on flow quantities during the solution process. We represent this macro using only one argument. This argument indicates the name of the function. To activate this function and link it to the software, you need to navigate to this path and define the function as a UDF for the software. It is worth mentioning that the UDF in question appears in the Fluent software with the same name that we defined in the first argument of the define macro. To activate the UDF function, you first need to call the desired UDF function in the Fluent software. Then go to the part of the software environment where the UDF function is to be applied, and finally activate the called UDF at the appropriate place. So first, go to define in the header, then to user defined and select the function option, and from the appearing menu select compile. By doing this, the desired UDF function is called in the Fluent software. Then in the same user defined section, select function hooks. Now in the appearing menu, go to the execute at end option, and in the section select and activate the called UDF function. In another example, we examine the define init macro. This macro is used to create the desired initial conditions in the model. In fact, this macro performs a similar operations to patch, but does it differently and using a UDF. Also, the function of this macro is executed once in each initialization and is called immediately after the default initialization is performed by the software solver. This macro is represented using two arguments. The first argument indicates the function name, and the second one is a pointer to the model's domain on which the initialization function is applied. That is, this domain pointer allows access to the information of all cells and third surfaces in the desired computational domain mesh. To activate this function and link it to the software, you need to navigate to this path and define the function as UDF for the software. It should be noted that the UDF in question appears in Fluent software with the same name we defined in the first argument of the defined macro. To activate the UDF function, you first need to invoke the desired UDF function in Fluent software. Then go to a part of the software environment where the UDF function is to be applied, and finally activate the invoked UDF in the appropriate place. So first, go to the user defined section. From the define header, select the function option, and from the appeared menu, select the compile option. By doing this, the desired UDF function is invoked in Fluent software. Then in the same user-defined section, select the function hooks option. Now in the appeared menu, go for the initialization option so that in this section you can select and activate the invoked UDF function. Now we are going to introduce another group of macros. In this section we intend to introduce the model-specific defined macro. These macros are used to set parameters for a specific model in ANSYS Fluent. Here we introduce a few examples of defined macros specific to numerical models. Profile macro. This macro is used to define boundary conditions. For example, it is used to define pressure, velocity, and temperature variations at the inlet and outlet boundaries, or wall thermal conditions like heat flux variations, heat transfer coefficient, and heat generation rate, and many other cases. Property macro. This macro is used to define material properties. For example, it is used to define variations in density, viscosity, thermal conductivity, and other required thermophysical properties. Source macro. This macro is used to define desired source terms in solving different transport equations. For example, it is used to define source terms related to mass, momentum, energy, and other required equations. Parental macro. This is used to define the parental number. For example, it is used to define the parental number related to the questions of kinetic energy or the dissipation rate of the K epsilon turbulence model. Diffusivity macro. This macro is used to define the diffusion or dispersion of species or any user-defined scalar. VR rate macro. This macro is used to define the reaction rate when using chemical reaction equations. A very common example of macros in this category is the define profile macro. This macro is used to specify a certain boundary profile or a cell zone condition that changes as a function of spatial coordinates or as a function of time. Here are a few examples of the uses of the profile macro. Velocity, pressure, temperature, turbulent kinetic energy, and turbulent dissipation rate variations as a function of time or spatial coordinates. Mass flow rate variations as a function of time. Species mass ratio variations when using the species transport model. Phase volume ratio variations when using the multiphase model. Wall thermal conditions variations like wall temperature, imposed wall heat flux, heat generation rate in the wall heat transfer coefficient, and etc. And many other cases. This macro is represented using three arguments. The first argument indicates the name of the desired function. The second argument is a pointer to a thread where the desired function the boundary condition should be applied to its surfaces. The third argument represents an index that specifies the variable to be defined. In other words, the index specifies which variable the desired function should act upon. Alternatively, this argument represents the index that each of the surfaces of a surface thread must traverse so that the function is applied to all these surfaces. To activate this function and link it to the software, you need to go to this path and define the function as a UDF for the software. It's worth mentioning that the UDF appears in Fluent software with the same name that we defined in the first argument of the defined macro. To activate the UDF, you first need to call your desired UDF in Fluent software. Then go to the part of the software environment where the UDF is to be applied, and finally activate the called UDF in the appropriate place. So first, go to the Define tab, then to User Defined, select Functions, and from the appearing menu, choose Compile. This will call the desired UDF in Fluent software. Now, suppose the UDF is related to a velocity change profile at the inlet boundary. So, go to the boundary condition settings, and for the desired boundary, select the velocity inlet boundary condition. In the section where you need to specify the velocity, select UDF profile. Finally, select and activate the called UDF. Another widely used example of macros in this group is the define property macro. This macro is used to change or define the value of specific thermophysical properties of materials. For instance, suppose you intend to define the value of various thermophysical properties such as fluid density, fluid viscosity, thermal conductivity coefficient, etc. as a specific function. If we use spatial models in Fluent, we can also define other thermophysical properties using these macros. For example, the value of the absorption and diffusion coefficient when using the radiation model, or the value of the surface tension coefficient between phases when using the VOF multiphase model, or the size of particle and droplet diameters when using the mixture multiphase model, and etc. are among these cases. These macros are represented using three arguments. The first argument indicates the name of the desired function. The second argument is an indicator of the cell index. It specifies a cell from a particular cell string for the desired function to be applied to. The third argument is a pointer to that cell string that the desired function should apply to its cells. To activate this function and link it to the software, you need to go to this path and define the function as a UDF for the software. It's worth mentioning that the UDF we define appears in Fluent software under the same name we defined in the first argument of the define macro. To activate the UDF function, you first need to invoke the desired UDF function in Fluent software. Then go to a part of the software environment where the UDF function is to be applied. And finally, activate the invoked UDF in the appropriate place. So first, go to the define header, then go to user defined, select the function option, and from the appeared menu, select compile. By doing this, the desired UDF function is invoked in Fluent software. Now suppose the UDF function is related to the value of one of the thermophysical properties like density. So go to the materials settings section, and for the desired property, select the user defined option. Finally, select and activate the invoked UDF function. Another commonly used example of this macros is the define source macro. This macro is used to specify and define source terms in each of the transport equations. During the solution process, various transport equations are solved by the solver, including continuity, momentum, energy, or turbulence equations like K and epsilon, or species mass fraction transport equations, and so forth. These macros are represented using 5 arguments. The first argument indicates the name of the desired function. The second argument is an indicator of the cell index in such a way that it specifies a cell from a certain cell thread for the desired function to be applied on. The third argument is a pointer to that cell thread that the desired function should be applied to its cells. The fourth and fifth arguments are respectively the derivative of the source term expression and the number of the desired equation. In fact, the derivative of the source term with respect to the dependent variable is used to linearize the source term and to increase the numerical solution stability. To activate this function and link it to the software, you should go to this path and define the function as a UDF for the software. It should be noted that the desired UDF appears in the Fluent software with the same name that we defined in the first argument of the define macro. So first go to the define tab, then to user defined section and select function. From the appearing menu, select compile. By doing this, the desired UDF function is called in the Fluent software. Now, suppose the UDF function is related to an energy source term for use in the energy equation. So, go to the cells and conditions settings and enable source terms to provide the ability to add source terms to the transport equations. Then go to the source term settings tab and for the desired equation enable a source term number. Finally, select and activate the called UDF function. As another example of these types of macros, we introduce the define parental macros. These macros are used to specify the parental number related to the turbulence equations that are solved by the Fluent solver. In fact, in the equations related to the K epsilon turbulence model, a parental number is used for which a specific function can be used to define it. Of course, parental macros are made up of different types. For example, the define parental D macro is used to define the parental number related to the turbulence energy dissipation equation. The define parental K macro is used to define the parental number related to the kinetic energy equation. The define parental O macro is used to define the parental number related to the specific dissipation equation, and the define parental T macro is used to define the parental number related to the diffusion term of the temperature equation. To examine the arguments, we consider the define parental K macro. This macro is represented using 3 arguments. The first argument indicates the name of the desired function. The second argument is an indicator of the cell index. It specifies a cell from a specific cell thread so that the desired function can be applied to it. The third one is a pointer to the cell thread that the desired function should be applied to its cells. To activate this function and link it to the software, you need to go to this path and define the function as a UDF for the software. It should be noted that the UDF in question appears in the Fluent software with the same name that we defined in the first argument of the define macro. So, first go to the define header, go to the user defined function section, select the function option, and from the appearing menu, select compile. By doing this, the desired UDF function is called in the Fluent software. Now, suppose the UDF function is related to the parental number in the turbulence kinetic energy equation. So go to the viscous model settings section and select the desired turbulence model. This turbulence model consists of 2 equations, including the turbulence kinetic energy equation and the energy dissipation rate. To define the parental number of the turbulence kinetic energy equation, go to the TKE parental number section. Finally, select and activate the called UDF function. This time we are introducing another category of macros. Some of the defined macros are specific to multiphase models. That is, they are used in multiphase flows. There are many macros specific to multiphase models and they are used in many applications. Here, you will observe a few of examples of commonly used macros that are used in various multiphase models. The cavitation rate macro, which is used to estimate the cavitation rate. However, this macro is only used for the multiphase mixture model. The exchange property macro, which is used to define changes in property such as drag change coefficient, drag correction factor, lift coefficient, and etc. However, this macro is used for multiphase mixture and Eulerian models. The vector exchange property macro, which is used to define the slip velocity. However, this macro is only used for the multiphase mixture model. The mass transfer macro, which is used to estimate the mass transfer rate between phases. This macro is used for all multiphase models including VOF, mixture, and Eulerian. The linearized mass transfer macro, which is used to estimate the mass transfer rate. This macro is also used for all multiphase models including VOF, mixture, and Eulerian. Now let's examine a few examples of these multiphase macros. For instance, the defined cavitation rate macro is used to model the cavitation source terms in the vapor mass fraction transfer equation. This macro is used to estimate the phase change rate between liquid and vapor when cavitation occurs. The cavitation model used in this equations is the single model. According to this cavitation model, the relationship for estimating the cavitation source terms is expressed as follows. These relationships are based on the mass transfer rate between the liquid and vapor phases and the mass fraction of each of the liquid and vapor phases. This macro is represented using several arguments. The first argument indicates the name of the function. The second one represents the cell index, and the third argument is a pointer to the thread of cells related to the mixture flow that the function should be applied to. The fourth argument is a pointer to the common pressure of liquid and vapor. The fifth and sixth arguments are pointers to the vapor phase density and liquid phase density respectively. The seventh argument is a pointer to the vapor mass fraction. The eighth argument is a pointer to the vapor pressure, also known as the evaporation pressure. The ninth and 10th arguments are pointers to the liquid surface tension coefficient and the mass fraction of non-condensable gases, respectively. Finally, the 11th argument is a pointer to the cavitation mass transfer rate, which is also known as the cavitation rate. To activate this function and link it to the software, you need to go to this path and define the function as a UDF for the software. It should be noted that the UDF in question appears in Fluent software under the same name that we defined in the first argument of the define macro. So, first go to the define in the menu bar, then user defined and select functions. From the drop down menu, select compile. This will call the desired UDF function in Fluent software. Now, to use the UDF related to the single cavitation model, you must definitely use the mixture multiphase model. So first, go to the multiphase model settings and activate the mixture multiphase model. After defining the liquid and vapor phases for the mentioned two-phase flow, go to phase interaction and then the heat mass reaction tab. Now you should activate the single atoll cavitation model option. By doing this, you are allowed to define the UDF function related to the single cavitation model. However, the option related to the single model does not exist by default in the settings of the phase interaction section. You should enter the command solve set expert in the Fluent software console window, and then in response to the phrase use single atoll cavitation model, enter yes. Finally, after performing the mentioned tasks from the same user defined section, select function hooks Now in the appeared menu, go to the cavitation mass rate option, so that in this section you can select and activate the called UDF function. In another example, we introduce the define exchange property macro. This macro is used to estimate variables related to the interaction or confrontation between phases in multiphase models. In fact, these interfacial variables result from the collision of two different phases with each other in multiphase flows. Variables such as the drag change coefficient, drag correction factor, volumetric heat transfer coefficient, virtual mass coefficient, lift coefficient, lubrication coefficient, and interfacial area are among these interfacial variables. These macros are also represented using several arguments. The first argument indicates the name of the desired function. The second argument is an indicator of the cell index, and the third argument points to the cell thread related to the mixed flow that the desired function should be applied to its cells. The fourth and fifth arguments respectively indicate the index of the primary and secondary phases in the desired multiphase flow. In fact, they specify the primary and secondary phase of the phase pair for which you intend to apply a phase interaction property. To activate this function and link it to the software, you should go to this path and define the function under the title UDF for the software. It should be noted that the UDF in question appears in Fluent software with the same name that we defined in the first argument of the define macro. So first, go to the define header, then go to the user defined section, select the function option, and from the drop down menu select the compile option. By doing this, the desired UDF function is invoked in Fluent software. Now, suppose the UDF function is related to estimating the drag coefficient between two phases. So go to the multiphase model settings section to define your desired multiphase model. After determining the type of multiphase model, for example VOF, and specifying the phases present in the two-phase flow, go to the phase interaction section. In this section, go to the force header, and in the drag coefficient section, select the user-defined option. Finally, select and activate the invoked UDF function. In another example, we introduce the define mass transfer macro. This macro is used to model mass transfer in a multiphase problem. The mass transfer rate specified using this macro is used to calculate mass, momentum, energy, and species sources for the phases involved in mass transfer. It should be noted that the species transport issues, mass transfer will occur from one species in one phase to another species in another phase. This macro is represented using several arguments. The first argument indicates the name of the desired function. The second one represents the cell index, and the third argument points to the cell thread associated with the mixed flow that the desired function should be applied to. The fourth argument represents the phase index from which mass transfer occurs, and the sixth argument represents the phase index to which mass transfer occurs. The fifth argument represents the species from which mass transfer occurs, and the seventh argument represents the species to which mass transfer occurs. To activate this function and link it to the software, you should go to this path and define the function as a UDF for the software. It is worth mentioning that the desired UDF appears in Fluent software with the same name we defined in the first argument of the define macro. So, first, go to the define menu, select the user defined section, and choose function. From the appearing menu, select compile. By doing this, the desired UDF function is called in Fluent software. To define mass transfer between two phases, you need to define a multiphase flow. So go to the multiphase model settings to define the desired multiphase model. After determining the type of multiphase model, for example VOF or mixture, and specifying the phases present in the two-phase flow, go to the phase interaction section. In the section, go to the heat mass reactions tab, and in the mass transfer mechanism section, select user defined. Finally, select and activate the called UDF function. There is another category, defined macros, that are specific to discrete phase models. The number of macros in this category is also high. Here we introduce a few examples of the more commonly used in this category. DPM BC macro. This is used to express the state or behavior of discrete particles at the desired boundary. DPM drag macro. This is used to estimate the drag coefficient between particles and fluid. DPM erosion macro. This is used to estimate the erosion rate and cohesion. DPM property macro. This is used to define the thermophysical properties of the material related to discrete particles. DPM time step macro. This is used to control and adjust the time step in discrete phase simulations. DPM source macro. This is used to express the source terms of particles in equations related to discrete particles. DPM body force macro. This is used to estimate the body force on particles. Now, among the introduced macros, we will examine a few examples. For instance, the defined DPM BC macro is used to set boundary conditions for discrete particles present in the computational domain. When discrete particles reach a boundary of the computational domain, they can exhibit different behaviors. These particles can simply pass through the desired boundary or reflect after collision, or be trapped at the same location. Using this macro, we can apply the desired behavior to the discrete phase. The desired behavioral function is executed whenever a particle reaches a boundary of the computational domain and comes into contact with it. This macro is represented using 6 arguments. The first argument indicates the name of the desired function. The second argument is a pointer to a data structure that contains information about the tracked particle. The third one is a pointer to a surface thread of discrete particles that are colliding. The fourth argument is the index of that surface from the desired surface thread of discrete particles that are colliding. The fifth one represents the unit normal vector, or perpendicular to the surface. The sixth argument indicates the dimensions of the problem under consideration. These dimensions can be expressed in 2 or 3 dimensions. To activate this function and link it to the software, you need to navigate to this path and define the function as a UDF for the software. It should be noted that the UDF in question appears in Fluent software under the same name that we defined in the first argument of the define macro. So first, go from the define header to the user defined section. Select the function option and form the displaced menu. Choose compile, and by doing this, the desired UDF function is invoked in Fluent software. Now, go to the discrete phase model settings section and define an injection to specify the desired discrete particle flow. When the discrete phase model is activated, the DPM tab appears in the boundary condition settings section. Now, to define the type of state of behavior of discrete particles in the discrete phase boundary condition type section, select the user defined option, and finally select and activate the invoked UDF function. In another example, the defined DPM drag macro is used to determine the value of drag coefficient between particles and fluid. That is, with this macro we can estimate the value of the drag coefficient between discrete particles and continuous fluid. According to the presented relation, the drag coefficient between particles and fluid is represented in the form of a dimensionless expression. This macro is represented using three arguments. The first argument indicates the name of the desired function. The second one represents the Reynolds number of the particle in terms of the particle diameter and the relative fluid flow velocity. The third argument points to a data structure that contains information about the tracked particle. To activate this function and link it to the software, you need to go to this path and define the function as a UDF for the software. It should be noted that the UDF in question appears in Fluent software with the same name that we defined in the first argument of the define macro. First, go to the define header, then the user defined section and select the function option. And from the appeared menu, choose compile. By doing this, the desired UDF function is called in the Fluent software. Now, go to the discrete phase model settings and define an injection to define the desired discrete particle flow. In the injection settings, go to the physical model header and then the drag law settings. Finally, select and activate the called UDF function. In another example, the define DPM erosion macro is used to determine the calculated erosion and cohesion rates when a particle flow hits a wall surface or collides with a porous jump surface. That is, when particles collide with a solid surface, it's possible that the surface in question may be subject to the phenomenon of aberration. It should be noted that this function is called when a particle encounters a reflective surface. This macro is represented using several arguments. The first argument indicates the name of the desired function. The second argument is a pointer to the data structure that contains the information related to the tracked particle. The third argument is a pointer to a surface thread of discrete particles that are colliding. The fourth one is the index of that surface from the surface thread of discrete particles that are colliding. The fifth argument is an indicator of the unit normal vector or perpendicular to the surface. The sixth argument indicates a variable that shows the collision angle between the particle path and the surface. The seventh argument indicates a variable that represents the magnitude of the particle speed. The eighth argument indicates the mass flow rate of the colliding particle. If the flow is steady, this argument represents the current mass flow rate of the particle flow for the number of random atoms during collision with the surface. And if the flow is transient, it represents the mass of the package colliding with the surface. To activate this function and link it to the software, you should go to this path and define the function as a UDF for the software. It should be noted that the UDF in question appears in Fluent software with the same name that we defined in the first argument of the define macro. First, go to the define tab, then to user defined, select function, and from the appeared menu, select compile. By doing this, the desired UDF function is called in Fluent software. Now, go to the discrete phase model settings and define an injection to define the desired discrete particle flow. Then, in the discrete phase model settings, go to the physical model tab and enable the erosion accretion option. When you enable this option in the UDF tab, the erosion accretion option also appears for the user defined function section. Finally, select and activate the called UDF function. Another category of macros that are widely used in Fluent software is the define macros used in the dynamic mesh model. We use the dynamic mesh model when a boundary or area of a computational domain is deforming or moving. The use of UDF programming with related macros facilitates these deformations or displacements of boundaries and regions. Here you see a few examples of macros used in the dynamic mesh model. CG motion macro, which is used to define a translational or rotational motion of the object's center of gravity. SDOF properties macro, which is used to define the characteristics related to the 6th degree of freedom solver. grid motion macro, which is used to define the mesh movement, i.e. different points or regions of the model grid undergo movement. GM macro, which is used to define how the cell layer height changes. Dynamic zone property macro, which is used to define how the geometric shape changes. Contact macro, which is used to define contact detection, i.e. For when a moving surface gets close to a stationary surface and is on the verge of contact. Now, let's examine a few examples of macros from the dynamic mesh category. For instance, the define CG motion macro is used to define the motion of a dynamic zone in the computational domain of the model. Using this macro, we can define a dynamic motion with a specified translational or rotational velocity at each time step of the solution process. ANSYS Fluent software uses these velocities to update the spatial position of the concerned zone as a rigid body motion. This macro is represented using 5 arguments. The first argument indicates the name of the desired function. The second argument is a pointer to a data structure that stores the specifications of the dynamic mesh. These specifications are either determined by the user or calculated by Fluent software. The third and fourth arguments, respectively, represent the translational and rotational velocity. The fifth and sixth arguments respectively indicate the current time of the model and the time step of the model. To activate this function and link it to the software, you need to go to this path and define the function as a UDF for the software. It's worth mentioning that the UDF appears in Fluent software with the same name that we defined in the first argument of the define macro. First, go to the define menu, then to the user defined section and select the functions option. From the appeared menu, select compile. By doing this, the desired UDF function is invoked in Fluent software. Now, go to the dynamic mesh settings to activate the dynamic mesh model. Then, go to the dynamic mesh zone settings and after selecting the desired boundary, activate the rigid body option so you can define the motion of the desired boundary as a rigid body. Now, in the motion attributes menu, go to the motion UDF profile section. Finally, select and activate the invoked UDF function. In another example, we introduce the define SDOF properties macro. Using this macro, you can specify the motion properties of moving objects for the 6th degree of freedom solver. These motion properties include mass, moments of inertia, constraints, external forces, and so on. In fact, an object within the computational domain can have freedom of movement in 6 directions. There are 3 translational degrees of freedom along the x, y, and z directions and 3 rotational degrees of freedom around the x, y, and z axis. This macro is represented using 5 arguments. The first one indicates the name of the desired function. The second argument is a pointer to an array where the 6 degrees of freedom motion characteristics are stored. The third argument is a pointer to a data structure that stores the dynamic mesh specifications. These specifications are either determined by the user or calculated by Fluent software. The fourth and fifth arrays are respectively indicative of the current system time and the model's time step. To activate this function and link it to the software, you need to go to this path and define the function under the title UDF for the software. It's worth mentioning that the UDF in question appears in the Fluent software with the same name we defined in the first argument of the define macro. First, go from the define header to the user defined section and select the function option. Then from the displayed menu, select the compile option. By doing this, the desired UDF function is called in Fluent software. Now, go to the dynamic mesh settings section to activate the dynamic mesh model. Since you intend to define a motion based on the degree of freedom, activate the 6DOF solver mode. Then go to the dynamic mesh zone settings section And after selecting the desired boundary, activate the rigid body option so that you can define the movement of the desired boundary as a rigid body. Now, in the motion attributes header, go to the 6DOF UDF properties section. Finally, select and activate the called UDF function. In another example, we examine the define grid motion macro. This macro is used when we intend to control the movement of a boundary based on the position of a geometric nodes that constitute it. That is, we control the movement of each node independently and separately. By default, ANSYS Fluent software considers the movement of a boundary or region within the computational domain as a rigid body. This means that all points and geometric nodes of that boundary or region move together, and there is no relative movement between the nodes. But sometimes we intend the nodes of a boundary or region to have relative movement to each other. In such cases, we use the grid motion macro. For example, during the creation of a beam or structural elements deflection, the spatial position of the nodes will vary. This macro is represented using 5 arguments. The first argument indicates the name of the desired function. The second argument is a pointer to the computational domain of the model. The third argument is a pointer to a data structure that stores the specifications of the dynamic mesh. These specifications are determined by the user or calculated by ANSYS Fluent software. The fourth and fifth arrays are respectively representative of the current system time and the model's time step. To activate this function and link it to the software, you need to go to this path and define the function as a UDF for the software. It should be noted that the desired UDF appears in the Fluent software with the same name that we defined in the first argument of the define macro. First, go to the define heading, then to the user defined section, select the function option, and from the menu that appears, select compile. By doing this, the desired UDF function is called in the Fluent software. Now, go to the dynamic mesh settings section to activate the dynamic mesh model. Then go to the dynamic mesh zone settings section, and after selecting the desired boundary, activate the user defined option so that you can define the movement of the desired boundary in terms of the position of different mesh points. Now, in the motion attributes heading, go to the mesh motion UDF profile section. Finally, select and activate the called UDF function. Previously, we introduced various define macros in full detail. These define macros are specifically for UDF programming and are defined in a way that they can be received by ANSYS Fluent software. And as part of the tutorial, we introduce other predefined macros that we can use when defining a UDF. In fact, writing a UDF program requires the use of other macros as well. The macros we intend to introduce include data access macros, loop macros, dimension and vector macros, time-dependent macros. And as part of the tutorial, we want to introduce macros that allow us to access data and information related to geometry, flow, and etc. during the solution process. This data and information are received by Fluent software. In fact, we intend to introduce various macros necessary for accessing Fluent data. These data access macros include node macros, cell macros, face macros, user-defined scalar macros, and user-defined memory macros. First, we examine the node macros. The computational mesh or grid of the model in ANSYS Fluent is defined by the spatial position of the nodes and the way they connect and relate to each other. The node macro represents the spatial position and coordinates of the nodes. That is, it provides the spatial position of the desired node in Cartesian coordinates. These macros consist of only one argument, which is a pointer to the node. The fn nodes macro indicates the number of nodes associated with the surface. These node counts are defined as integers. This macro consists of two arguments. The first argument represents a variable that is the place to receive information about each surface from the faith thread, and the second one is a pointer to the faith thread. Next, we introduce the cell macros. This group of macros represent the real value related to cell variables in SI units. The C-centroid macro provides the coordinate of the spatial position of the cell centers. This macro consists of three arguments. The first one represents the spatial position coordinates of the cell in terms of x, y, and z, which are presented as real numbers. The second argument represents a variable that is the place to receive cell information from a cell thread. And the third argument is a pointer to the cell thread. The C volume macro is a calculator for the volume of the cell. This macro consists of two arguments. The first one represents a variable that is the place to receive information about each cell from the cell thread, and the second one is a pointer to the cell thread. The CN nodes and CN faces macros respectively represent the number of surfaces related to a cell and the number of nodes related to a cell. These macros consist of two arguments. The first argument represents a variable that is the place to receive information about each cell from the cell thread, and the second one is a pointer to the cell thread. Cellular macros are also used to obtain the values of fluid flow variables in computational domain cells. We refer to a few examples of these macros. For instance, the CR macro represents the density of the fluid in the cell of interest. The CP macro represents the pressure in the cell. The CU, CV, and CW macros respectively represent the cell velocity in different directions. The CT macro represents the cell temperature. The CK and CD macros respectively represent the turbulent kinetic energy and specific dissipation rate in the turbulence model. These macros all consist of two arguments. The first argument represents a variable that is the place to receive information about each cell from the cell thread, and the second one is a pointer to the cell thread. However, the CYI macro represents the mass ratio of a species. This macro also has a third argument. The third argument indicates the index or counter of the species. In addition to accessing cell variables, the user can also access the gradient vectors of cell variables. Here we present several examples of cell gradient vector macros. For instance, the CP macro represents the gradient vector of cell pressure. The CTG macro represents the gradient vector of cell temperature. The CUG, CVG, and CWG macros respectively represent the gradient vector of cell velocity in different directions. These macros all consist of two arguments. The first one represents a variable that is the place to receive information about each cell from the cell thread, and the second one is a pointer to the cell thread. Note that if you intend to access each of the vector components of each variable, you should use the index I. The numbers 0, 1, and 2 are used respectively for x, y, and z. For example, these expressions are used to obtain the temperature gradient value in the direction of x, y, and z axis. A group of cell variable macros are introduced as previous time step macros. That is, they obtain the value of the variable in the cell at the previous time step. Therefore, this data can be useful in solving transient problems. For these macros, it's sufficient to use the M1 suffix. We have shown a few examples of these macros. For instance, the CRM1 macro represents the density value at the previous time step. The CTM1 macro represents the temperature value at the previous time step. The CPM1 macro represents the pressure value at the previous time step. The CUM1 macro represents the velocity value in the x-axis direction at the previous time step. This macros also consists of two arguments. The first argument represents a variable that is the place to receive information about each cell from the cell thread, and the second argument is a pointer to the cell thread. Now, if we use the em2 suffix for cell variable macros, it retrieves the variable value 2 times a step back. Similarly, the CRM2 macro represents the density value 2 times steps back. The CTM2 macro represents the temperature value 2 times steps back. The CPM2 macro represents the pressure value 2 times steps back, and the CUM2 macro represents the velocity value in the x-axis direction 2 times steps back. Another group of cell macros exists that are used to calculate the derivative values of velocity. Here we have presented a few examples of these velocity derivative macros. For instance, the CDUdx macro represents the derivative value of velocity in the x-axis direction with respect to the x-spatial coordinate in computational domain cells. That is, it's equivalent to the expression du dx. In another example, the CdVdz macro represents the derivative value of velocity in the y-axis direction with respect to the z spatial coordinate. That is, it's equivalent to dvdz. In yet another example, the CdWdy macro represents the derivative value of velocity in the z-axis direction with respect to the y spatial coordinate. That is, it's equivalent to dwdy. In these macros too, there are two arguments. The first one represents the variable receiving cell information, and the second one points to the cell thread. Some of the cell macros are used to calculate the actual value of fluid properties. All values are presented in SI units. Let's examine a few examples of these macros. For instance, the CMUL macro represents the value of laminar viscosity in computational domain cells. The CCP macro indicates the value of specific heat, and the CKL macro indicates the value of thermal conductivity. The CR gas macro represents the universal gas constant. The CLIOF macro indicates the mass ratio of liquid in a cell. The ABS-COEF macro indicates the absorption coefficient. All these macros also consist of two arguments. The first one represents the variable receiving cell information, and the second one points to the cell thread. Here we present another group of macros related to the Reynolds stress values in turbulence models. These values are provided in SI units. Let's examine a few examples of these macros. For instance, the CRUU macro is equivalent to the Reynolds stress term in the form of UU, velocity in the x direction multiplied by velocity in the x direction. The CRUV macro is equivalent to the Reynolds stress term in the form of UV, or velocity in the x direction multiplied by velocity in the y direction. The CRVW macro is equivalent to the Reynolds stress term in the form of VW, velocity in the y direction multiplied by velocity in the z direction. These macros also consist of two arguments. The first one represents the variable receiving cell information, and the second one points to the cell thread. Here we introduce another cell macro that is specific to the volume of fluid multiphase model. The CVOF macro represents the volume fraction for the phase that is located in the specific cell thread. And now we introduce this phase macros. This group of macros represent the actual value related to the cell surfaces in SI units. However, it should be noted that these macros are only usable in a pressure-based solver. The F-centered macro represents the coordinate of the spatial position of the center of the desired surface. This macro consists of three arguments. The first argument represents a variable that receives the spatial position coordinates of the desired surface. In fact, when we have a surface, its x, y, and z components have a certain range. The value in this range are received in a variable named x, so that the mentioned macro can find the median value of each of these ranges. The second argument represents a variable named f that receives data related to each of the surfaces. That is, there are multiple surfaces in a surface thread, and when we traverse each of the surfaces in this thread, the data of that surface is dumped into the f variable. And the third one is a pointer to the existence of a surface thread. The f area macro is used to obtain the area vector for a specific surface. The area vector refers to a vector perpendicular to the surface area. This macro also consists of three arguments. The first argument represents a variable that receives the spatial position coordinates of the desired surface. The second argument represents a variable named f that receives data related to each of the surfaces. And the third one is a pointer to the existence of a surface thread. A group of surface macros is related to the flow variable values on the boundary surfaces. That is, these macros provide access to flow variables on a boundary surface. We introduce a few examples of these macros. For instance, the FU, FV, and FW macros represents the speed value in the X, Y, and Z directions, respectively. The FT and FH macros represent the temperature and enthalpy values, respectively. The FK and FD macros, respectively, represents the value of turbulent kinetic energy and rate of turbulent energy dissipation. These macros consist of two arguments. The first one represents a variable f that receives data from each of the surfaces of the surface thread, and the second one is a pointer to the desired surface thread. We also have the FYI macro, which is used to represent the mass ratio of species. In this macro, the argument I is equivalent to the index or counter of the desired species. The previous macros are only used on boundary surfaces. Another group of macros is related to the flow variable values on both internal and boundary surfaces. Among these macros, we can mention the FP macro, which represents the pressure value on the desired surface, and the F-flux macro, which represents the max flow rate passing through the desired surface. These macros also consist of two arguments. The first one represents a variable f that receives data from each of the surfaces of a surface thread, and the second one is a pointer to the desired surface thread. Now it's time to introduce macros specific to the transport equations of user-defined scalars. Suppose you intend to add a scalar variable to your modeling process and define a specific equation for that variable so that the software solves the desired scalar equation. For instance, the FUDSI macro is used to access the value of surface variables calculated for user-defined scalar transport equations. This macro consists of three arguments. The first argument represents a variable f that receives data from each of the surfaces of a surface thread. The second argument is a pointer to the desired surface thread, and the third one is the counter or index of the desired scalar. In another example, the CUDSI macro is used to access the value of cell variables calculated for user-defined scalar transport equations. This macro consists of three arguments. The first argument represents a variable C that receives data from each of the cells of a cell thread. The second one is a pointer to the desired cell thread, and the third argument is the counter or index of the desired scalar. Furthermore, the CUDSI-G macro is used for the gradient of the desired UDS, and the CUDSI-M1 macro is used for the value of the desired UDS at a previous time step. Similarly, these macros consist of three arguments. Finally, it's time to introduce macros related to user-defined memory variables. Some macros are associated with variables that are stored in user-defined memory. In fact, suppose you intend to store information in a memory-defined variable during the solution process. In other words, suppose you want to access the value of a function or variable during the software calculations, but this function or variable is not among the default variables defined by the software. By defining a UDM, this function or variable becomes accessible in the Fluent software results section. For example, the FUDMI macro is used to store data from a desired face in a user-defined memory. These macros consist of 3 arguments. The first argument represents a variable f that receives data from each of the faces of a face thread. The second argument is a pointer to the desired face thread. The third one is the counter or index of the desired memory, i.e. it specifies the memory location where the data should be stored. The CUDMI macro is also used to store data from a desired cell in a user-defined memory. These macros consist of 3 arguments. The first argument represents a variable C that receives data from each of the cells of a cell thread. The second argument is a pointer to the desired cell thread. And the third argument is an index that specifies the memory location where the data should be stored. And as part of the tutorial, we are going to introduce macros that can be used to create loops. These macros are known as loop macros. Loop macros are used to perform repetitive operations on cell or surface strings in the computational domain of a model. Therefore, ANSYS Fluent software has prepared a set of predefined macros for users to perform the task of creating loops. Here we introduce 2 general categories of loop macros. The first type of loop macros begins with the statement begin and ends with the statement end. These macros are applied to cells and surfaces present in the thread and calculate and execute the function defined within brackets for each surface or cell. While the second type of loop macros operate on multiple different threads and include a single statement, not in pairs with begin and end, and execute the operation specified within brackets. Now we will discuss different types of loops. Thread loop C is used when the user intends to execute a computational loop over all cell threads in a specific computational domain. Similarly, thread loop F is used when the user intends to execute a computational loop over all face threads in a specific computational domain. These macros consist of 2 arguments. The first argument refers to the face or cell thread that loop is to be executed on. The second one refers to the computational domain in which the face or cell threads are located. The begin and end C loop is used when the user intends to execute a computational loop on all cells in a specific cell thread. Similarly, the begin and F loop is used when the user intends to execute a computational loop on all faces in a specific face thread. These macros consist of 2 arguments. The first argument selects the desired face from the face thread or the desired cell from the cell thread. The second argument refers to the face thread or cell thread on which the loop is to be executed on its faces or cells. The C face loop is used when the user intends to execute a computational loop over all the faces of a specific cell. The C node loop is used when the user intends to execute a computational loop over all the nodes of a specific cell. The F node loop is used when the user intends to execute a computational loop over all the nodes of a specific face. These macros consist of 3 arguments. The first argument refers to the cell or face that the loop is to be executed on. The second argument refers to the target cell or face thread. The third argument is a local counter or index that either specifies the face number within the cell, selects the node number within the cell, or selects the node number within the face. In this section of the tutorial, we want to introduce macros known as vector and dimension macros. Fluent software has defined these macros to be used by users to access or manipulate vector quantities and deal with 2 or 3 dimensional analysis. In these macros, the expression v represents a vector, the expression s represents a scalar quantity, and the expression d represents a state in which a 3-component vector quantity is used in a 2-dimensional space, i.e., its third component is ignored. Now let's examine the macros related to 2 or 3 dimensionality. In general, the UDF program can be used for 2 or 3 dimensional solutions. Therefore, there are 2 methods in the UDF program to work with expressions that can be 2 or 3 dimensional. In the first method, we use an explicit method to divide program expressions into 2-dimensional and 3-dimensional parts. That is, separate code sections are compiled for 2-dimensional and 3-dimensional states. For this purpose, we use the if condition statement and rp2d and rp3d commands to divide the desired program into 2-dimensional and 3-dimensional parts. If we use one of the rp2d and rp3d macros in an if conditional statement, the program will be divided into 2-dimensional and 3-dimensional parts. For example, in this example, when you use this rp3d command, it means that rotational terms are only calculated if they are 3-dimensional calculations. In the second method, we need to consider expressions in a general 3-dimensional state in the UDF program and write them. Then, using the nd and mv macros, we can remove the third component of the vector during the compilation of 2-dimensional models. Therefore, using nd and mv macros in the UDF program allows you to include general 3-dimensional expressions in your code and remove the z component of the vector during 2-dimensional compilation. However, there is a difference between nd and mv macros. NV macros operate on vectors, while ND macros operate on individual components. That is, for ND, each component must be defined as an argument, while for MV, vectors considering of multiple components must be defined as arguments. In this section, we introduce ND macros. The constant nd underline nd is defined as 2 for 2-dimensional solutions and 3 for 3-dimensional solutions. And the underline nd can be used to create 2 multiple 2 or 3 multiple 3 matrices. The nd sum macro is used to calculate the sum of arguments. It means that the values of the components are added together. If the model is 2-dimensional, the values of x and y are added together, and if the model is 3-dimensional, the values of x, y, and z are added together. The nd set macro is used to equate expressions. It means that u is equal to the value of velocity along the x-axis, v is equal to the velocity along the y-axis, and w is equal to the velocity along the z-axis. Now let's examine NV macros. The NV underline v macro performs a mathematical operation on 2 vectors. It means that the different components of 2 vectors are equal to each other, so that the first element of vector is equal to the first element of vector x, and other components do the same. The NV underline v macro performs a mathematical operation on vector elements. It means that the elements of one vector are equal to the sum of the elements of 2 other vectors. That is, the first element of vector is equal to the sum of the first elements of vectors x and y. Other equations for other components are also in this order. Of course, this mathematical operator is an addition sign. This is while other mathematical operators such as multiplication, division, and subtraction can also be used. The NV underline v underline vs macro is used to add a vector to another vector that has been modified by a scalar. It means that the elements of one vector are equal to the sum of the elements of a simple vector and a vector modified by a scalar. That is, the first element of a vector A is equal to the sum of the first elements of vectors x and y multiplied by a specific scalar. Other equations for other components are also in this order. Now we want to introduce some vector functional macros. These macros allow an operation to be performed on vectors. For example, the nvmag macro is used to calculate the size of a vector. It means that the different components of vector x are raised to the power of 2 in different directions and added together, and the square root of the resulting value is taken. The nd dot macro is used to calculate the dot product of vectors. It means that the corresponding components of two different vectors, i.e. x component with each other, y component with each other, and z components with each other, are multiplied by each other, and ultimately the resultant values are added together. The nv dot macro also works similarly to the nd dot macro. That is, it performs the same mathematical operation, with the difference that in nd macros all components are defined as separate arguments and mathematical operations are performed directly on the argument themselves. But in nv macros, vectors are defined as arguments and mathematical operations are performed on the components of the arguments. The nd cross macro is used to calculate the cross product of vectors. Unlike dot product of vectors whose answer appears as a number, in cross product of vectors the answer appears as a vector. Therefore, the resultant vector consists of three components. To calculate each component of the resultant vector, we use the nd cross macro. For example, to estimate the value of x component of a vector resulting from cross product, we use nd cross x macro, whose formula for calculating it is shown. And in this section, we want to introduce another category of macros that includes time-dependent macros. For example, the current time macro represents the current time in seconds. The current time step and previous time step macros represent the current and previous time step values, respectively. The previous time and previous two time macros represent the previous time and the time 2 steps ago, respectively. The n time and n iter macros represent the number of time steps executed so far and the number of calculational iterations so far, respectively. All times are expressed as real numbers and counts are expressed as integers. Okay, we have come to the end of the UDF programming concepts tutorial in ANSYS Fluent software. In the end, it is necessary to remind 2 points to complete our training. The first point: the UDF programming language is written based on the C or C++ programming language. Therefore, you can use the concepts of these languages and some of their programming commands to better understand UDF coding. In this tutorial, we tried to focus on concepts that are mostly specific to Fluent software, so you can learn other concepts that have a more general aspect from other sources. For example, in this tutorial, we did not focus on various mathematical commands because these commands have a general aspect and you can easily learn these concepts from other educational resources. The second point: the concepts in UDF programming are very extensive and almost unlimited. For example, in UDF programming, you are faced with a very large number of types of macros. Naturally, teaching all of these macros is not a reasonable task, because firstly, there is not enough time to do this, and secondly, some of these macros are specific and learning them will be very difficult and confusing. Therefore, we tried to have proper management over the educational topics in this tutorial, so that we first try to provide all the basic concepts necessary for a complete understanding of UDF and then focus on teaching more useful concepts. In fact, Given our extensive experience in CFD work and simulation with ANSYS Fluent software, we try to teach common and useful macros in modeling. As a reminder, before the end of this session, it's necessary to have an overview of the discussed topics. These headings include the following: Chapter 1, Introduction to UDFs. Chapter 2, Training Examples, which contains CG Motion macro, Delta T macro, DPM drag macro, Initialization macro, Mass Transfer macro, Parental macro, Profile macro, Property macro, and Source macro. To benefit from Mr. CFD services, including simulation, consultation, and training, visit our website or contact us via info@mr-cfd.com.